Now, a rod of length 2L and mass m has a point mass 2m attached to its midpoint. This system is free to oscillate about a horizontal axis perpendicular to the length of the rod, through a point at which is a distance x from the point mass. Find the value of x for which the periodic time of small oscillations is a minimum. So we want to minimize the full system, okay? So what we can say here is that question 2. So we have a rod. This is the rod. It's off center C. On the center C, there's also a point mass here. So what's the mass of the rod on its own? M. Okay, so rod is M and length 2L. Point mass is 2M. So there's very much a localized 3M in there, isn't there? So we have the 2M mass and the M rod. Now, somewhere along this rod, the red line represents the rod, we fix an axis of rotation, and we denote this letter O. This axis of rotation is a distance x from the center of gravity of the rod, and also the point mass itself. Okay. So point mass, we're using md squared. So what's the point mass again? It's a moment of inertia about O through an axis that goes into the board, perpendicular to the plane of the board. Anybody? Md squared, so it's going to be 2m x squared. Now we're on to the rod. What's the rod's moment of inertia about its own center? It's 4 over 3 ml squared, provided it's of length 2L and mass m. Otherwise we'd have to modify it. Okay, following up on that, we're now going to use, perpendicular axis or parallel axis theorem? Why is it parallel axis theorem? Yeah, O and C are going into the board as opposed to on the plane of the board. Okay, so IO is going to be IC. Remember, it's usually plus MD squared, so it's going to be plus MX squared. Yes? Oh, it probably... Yeah, you're right, it is a third ML squared. Sorry guys, it's not 4, it's 1 over 3 because it's from its center, not from its endpoint, okay? Now, so I change IC into 1/3 ml squared. Okay. Now we're going to get our I total. What's I total, guys? I total is the rod added to the point mass. And what we're going to get there? 1/3 ml squared, yeah, plus, anybody? 3mx squared. Not 1 to like fractions being separated. I'm going to call that m bracket L plus 9x squared all over 3. Everybody happy enough with that? Okay. Now, what we're asked next is find the value of x for which the periodic time of small oscillations is a minimum. So, we're going to use our formula T equals 2 pi square root of I all over mgh. T equals 2 pi square root of, now this big lad here, so it's going to be m bracket L squared plus 9x squared over 3. Put that beside m. G. Can anybody tell me what h is? Anybody tell me what does h stand for again? It stands from the distance of your axis of rotation to the center of gravity of your object. and we know that to be x. Center of gravity, guys, located here. Axis of rotation, located there. Distance x away. So mgx. Now once we've done that, now imagine differentiating this not once but twice. A to find that it's a minimum, and then B to find that it's a max. A to find the turning point, first derivative. Second derivative then to prove if it's maximum or minimum. Seems like way too complicated for that. Okay, so here's what we're going to do instead. We're going to cross off those m's. They cross off anyway. We're going to square it out. Okay, so we get L squared plus 9x squared over x. Like, the maximum of t squared is the same thing as the maximum of t over 3gx. Now, I'm going to do that. Okay, can anybody explain why I broke it up that way? It's a constant times something that's differentiable. In fact, the 3 can go as well, can't it? So we'll get rid of the 3 as well. That 3 on the bottom can go over here. Okay? I'm going to rename this k, so that k equals L squared plus 6x squared all over x. Now here's the gist, guys. If I was to do to t dx, it gives the same x values as dt squared dx, which in turn gives the same x values as the k dx. The constants don't matter. Okay? First derivative equal to 0. Okay? So turning point, guys, first derivative equals 0. We're going to do the quotient rule, where u equals L squared plus 9x squared, v equals x. The u dx, guys, 18x. The v dx equals 1. Do the quotient rule for dk dx. And what we should get here is u phi times the u dx minus u times the v dx divided by x squared equals 0. Numerator is all what matters. It's going to be 18x squared minus 9x squared minus L squared equals 0. It's technically all over x squared as well, but we can cross multiply that x squared up so that it doesn't really matter in the solving of the equation. Now that that's done, we're then going to get L squared equals 9x squared. Finally calculate x. X squared equals L squared over 9. X equals L over 3. There we go. Now, is it a minimum? That's second derivative of that. Okay? So, did I even put down what the first derivative was? The first derivative is the first derivative was 9x squared minus L squared all over x squared. Okay, I'm going to second derivative this now. So I'm going to get that's dk dx. I'm going to get the second derivative now. So second derivative is u is 9k squared minus L squared. Du dx is 18x again. V is x squared. The v dx is 2x. So d2k dx squared ends up to be phi times du dx. So x squared times 18x minus u times the v dx. Now what did we say L was? X. Well, we had to substitute x in a second. So we're going to say it's u times the v dx. So 2x multiplied by 9x squared minus l squared. All divided by x squared. Now, 18x cubed minus 18x cubed plus 2xl squared all over x squared. Cancel, cancel. 2xl squared all over x, oh wait, x squared 2b squared, which is x to the power 4. 2l squared x to the power 3. X is defined as a distance away from the object. X has to be bigger than 0. L is the length of an object. L is defined as being bigger than 0. Therefore, the second derivative is bigger than 0 for all values of x and L. Therefore, it is a minimum. Alright? Cool. Or the other way, I suppose you could substitute in L over 3, can't you? To really make sure that x equals L over 3, so x cubed equals L cubed over 27. Put L cubed over 27 on the bottom. That's going to be 54 all over L. And 54 over L has to be bigger than 0 because L is guaranteed to be bigger than 0. Technically speaking, you could always argue that what happens if the x was over the other side? Does that not make it a negative? So to completely even rid that out of your head, x technically is defined as the magnitude away. It doesn't matter if it's positive or negative. But even at the end of the question, if you just substitute back in your L value, it then is definitively true because L is the length of a rod. Yes? No, it's not separable. So when you go up the top here, the L, and this is going to happen every time, is that the L is locked in a bracket with where is it here? The L is locked in a bracket with the x squared and has also been divided by x. So it's stuck in there. It's the only one you can't remove. Okay? And it's going to be like that for every question. Okay, we want to try another one. Question 4. Okay, guys. A uniform disk of mass m and radius r performs small oscillations in a vertical plane about a horizontal axis through a point which is distant x from the center. Find the period of time when x equals a half r. We have here is our circle. Center there, yeah. Now, what's going to happen next, guys, is we're told that it's of mass m and radius r. We'll call this c. Okay. It's then it's oscillating in a vertical axis. So if you imagine just holding a CD not by its center but by somewhere else on the CD, it just sort of can oscillate up and down. Okay. So what we're doing here is it doesn't matter what direction you put it in. Like if I said, oh, x is up here. Or sorry, axis O is up here, and that's distance x away here. That'd be acceptable, but what would be the really easy way of doing it? Keeping it horizontal. So what we can do instead is say, look, this axis O is over here, and it's the distance x away. Everybody happy enough with that? Now, we'll call it sig. IC is what, guys? The disk around its own center. What's its moment of inertia? A half mr squared. Okay. Now, what about IO? We're going to use perpendicular or parallel axis theory. It's going into the board. Remember, you're holding the circle by somewhere else not the center, but somewhere else on the circle itself. Parallel axis term, because we'll go 3D. We'll make it fancy. We're basically, that's C, and this one here is O, and it's rotating in this direction here, up, forward and back, forward and back, forward and back. Okay, or like that, forward and back, forward and back. Okay, so we're using parallel axis theory. C O. So a half IO equals a half MR squared, which is our IC value, plus MD squared, which is going to be, the distance is X, so it's going to be MX squared. Give them a common denominator. What do you think we should do? 2 M bracket the R squared plus X squared all over 2. Yeah, that's very easy, okay? Let's do the periodic time now. Yes, it is. 2x squared. And what we're going to say is time equals 2 pi square root of I all over mgh. Now, you could almost like give yourself an easy time and just square it right away. You could, but actually it wants the minimum time. It wants me to do something else before calculating the minimum. So I'll kill my jets there for a second. So what it wants me to do is it wants me to calculate the time it takes when x equals a half hour. So what is the periodic time? So it's 2 pi. Now if that's a half hour, what does that make this system here then? It's going to be m times r squared plus 2 times r over 2 squared all over 2. That's going to be r squared plus r squared over 2, which is 3r squared over 2. So it's going to be m times 3r squared over 2 divided by 2, which is 3mr squared all over 4. I'm going to put that in as my I value. Still not doing the differentiation question just yet. So then what we get is 3 over 4 mr squared. What's the m value? M is m, g is g. What's the h value? The h value refers to your distance of your axis to the center of gravity, usually defined as x, but we're told that x is a half r. So replace h with a half r. Okay. Okay. R cancels with r, m cancels with m. 6 over 4 is 3 over 2. 2 pi 3r over 2. It's that 2g, right? 2g. Okay. Now we're on the differentiation part, the part that's new to us. Okay. So the part that's new to us is would be starting back up here. Now, if this was just a differentiation question as opposed to anything else, I'd just square it straight away, save some time. T squared equals 4 pi squared I all over mgh. T squared equals 4 pi squared. Our I value there is m r squared plus 2x squared all over 2 m g. Now what's our h value again? H is always x in these ones. Once again, go back to the top if you don't understand why. Our axis of rotation's distance to the center of gravity of our object is x. Okay. Now, what's a constant and what's not a constant? T squared equals 2 constants to 2 pi squared. M's cancel. Put the G here. And then you have your differentiable part, r squared plus 2x squared all over x, marked in green. I'm going to call this any letter that I fancy. Doesn't matter what it is. I'm just going to stay with k for the time being. R squared plus 2x squared all over x. I got to calculate the x value, so I'm going to differentiate twice. Okay, so u equals r squared plus 2x squared. Du dx therefore is 4x. V equals x. dv dx equals 1. Use the quotient rule to find the k dx. So v by du dx minus u times the v dx all over v squared. 4x squared minus 2x squared. This is going to give me 2x squared minus r squared all over x squared. That is the first derivative. Might as well just put my head down and get the second derivative because I'm going to need it in a second. So I'll go again. Second derivative. And then what we're going to get this time. Phi times du dx, which is differentiating the top one, minus u times the v dx. The v dx is 2x, and that there is u. All over phi squared. The bottom one to be squared is x2 to the power 2. Second derivative, therefore, is the 4x cubed minus 4x cubed. When you multiply it out, it's going to be 4x cubed minus 4x cubed minus 2 r squared x plus 2r squared x. 2r squared x divided by x to the power 4 equals 2r squared all over x3. That's going to be guaranteed. That'll turn out to be bigger than 0 and hence a minimum because of whatever value we're going to find for x up here. Okay, let's go back to the top now. We never solved the first derivative equal to 0. So we're back in this neck of the woods and we're putting that equal to 0. We then get 2x squared minus r squared equals 0. R squared equals 2x to be squared. R equals the square root of 2x. Oh wait, I wanted x on its own. Nope, never mind. X squared equals r squared over 2. X equals r divided by root 2. Okay, grab that r divided by root 2. Bring it down here. So you get 2r squared divided by r over root 2 to be cubed. What are you going to get here? 2 root 2 on the bottom, so you're going to get 2r squared, r cubed, all over 2 root 2. Bring it up. Turn it upside down. So we're going to get 4 root 2 r squared over r cubed, which is 4 root 2 all over r. Has to be greater than 0 because r is always bigger than 0. It's the radius of a circle. Is that alright? Okay guys, so 6b. Deduce that the moment of inertia of a disk about a diameter is a quarter mr squared. Now, that is basically about its own diameter. We're so used to dealing with it going through dead center. We're so used to this. And that's what we've been basing our full chapter of, spinning like a CD, spinning around like a string or a rod of some sort. Okay. Now what you've also got to remember here is that there's a second option. The second option that it flips on its own diameter. Okay. So what we can define next is we can define this as the z-axis going upwards, and then we can define a x and y axis. I'll just do it like this for argument's sake, just to give it a bit of a 3D perspective. That's the y-axis, and this is the x-axis. But we're using the perpendicular axis theorem in reverse, such that iz equals ixx plus iyy. Is there any difference in xx and yy? Isn't it? It's because a circle is the same in every direction. If that was a rectangular lamina, a rectangle, would it make a difference? In a rectangle, ixx would be different from iyy. Yeah. Okay. And if it was a square, ixx would be the same as iyy. So therefore, a half mr squared is equal to two equal parts, i.e. it's the same as 2ixx or 2iyy. Ixx therefore is a quarter mr squared. That's you flipping it about its middle. If this was a circle, it'd be flipping like that. Okay? Now, the interesting part is, and the really tough part of moments of inertia is, how can you tell one question from the other from language alone? Okay? So it is very important. So, once we have a quarter mr squared, just remember that because we're going to use it in a minute. Now, might keep this where it is for a minute. Okay? Now, we would usually think that when we're doing... I'll need a rod. Give me a rod here. Give me a bit thicker. Grand. Okay, there's our rod there, and that's it. That's a different perspective on what's going on. Now, believe it or not, we would usually think that most of these questions are going down this way here. That the parallel axis term is parallel to the z-axis of the disk. Okay? But in this particular question, there's some language to suggest otherwise. The language that suggests otherwise is here. The plane of the disk passes through the axis of rotation. Plane of the disk passes through the axis of rotation. The full plane of the disk passes through the axis of rotation. Okay? So what we're doing is actually we're doing something like this. So where is it again? We're flipping it so it's going. Yeah. It's like this, and it's going on its side. So if you can imagine this coming out of the board and rotating, oh dear. If you can imagine this coming out and rotating back in behind, so it's a bit like this. Alright? That's the circle, that's the rod, and it's going like this. Plane of the disk passes through axis of rotation, as opposed to it's free to rotate in a horizontal axis, and then it's vertical to the axis of the board. So, plane of the disk, guys, refers to, if I was to extend the see my disk here, yeah? If I was to extend that, and if I was to extend that as a parallelogram in my 3D picture, like that, that's the plane of the plane of the disk. the disk is a two-dimensional object, and its plane is passes through the axis of rotation, and therefore the axis of rotation, it passes through all of it. Do you understand? All of the axis of rotation. So the axis of rotation could be this here, and therefore it has to spin around this axis here. So the full system keeps going up and around, up and around. Okay? If I was to draw that in 2D with this part here, it'd be that the plane of the disk would be like this, and that's my axis of rotation up here, and it comes out of the board like so, and then back around like that in 2D, and you're attached up here, so like that. Okay, so took me a while to figure out that just that little bit of word, through the axis. This passes through the axis of rotation, as opposed to what the previous questions were saying. Makes all the difference. Okay, now we're going to start off with setting up the systems. The hard part, the differentiation, is actually the easy part. Okay, so what's going on here? So the rod exists on both sides, doesn't it? It's not just one side, it actually exists on both sides. So, and it goes through the center of the circle. So the rod is going through the whole thing. So we'll make one more clone there. So that's basically the rod there. Okay, and it's going down and around. Now, let's calculate what's going on here. If I was to, what is parallel? Remember I highlighted this axis earlier. This axis here, and we're spinning around it. Can anybody give me an axis? Oh dear. Can anybody give me an axis that's parallel to that? Any axis that's parallel to that? The diameter, it was YY earlier, wasn't it? The diameter YY is roughly parallel. We can make an axis that's parallel to that axis there. So parallel to this one here would be YY going through there along the plane of the circle. Okay, along the plane of the circle. So that means that we can do it. We can do a C here. We can say IC is a quarter mr squared, provided your mass is m and your radius is r. What is it for my one? What's my IC for my circle? What's the weight of the circle, guys, or the mass of the circle? 24. What's its radius? A over 3. So I have to do a quarter 24m A over 3 squared. Okay, and when I do this, I'm going to get just 2 over 3. 2 over 3 MA squared. Now that's IC. I don't want IC. What do I want? What are we going to call this guy? I0. IO. We want IO. What type of term am I going to use for that? Parallel or perpendicular? Look at the two green axes. What do they look like? Parallel or perpendicular ones? They look parallel to each other. So we're going to use the parallel axis term. I0 equals IC plus MD squared. IO equals my 2 over 3 MA squared plus, what's the M value for this object? 24m. What is the distance between my two axes? Distance x, as shown on diagram. Distance x. Huh? Oh, the distance from my top line to my line going through the center of the circle. It's x. AC equals X, no? Sorry, just a lot of writing there, you're right, it's a bit confusing. AC equals X. The distance of my I-axis of rotation in red to my centre of the circle, diameter axis, is going to be X. Okay. It's a tough one. And now, we forgot one person in this whole thing. We've been working exclusively on the circle, haven't we? Haven't even gone near the rod yet. So that's all circle. This part here is just the circle about O. Has nothing to do with the rod. So now we're going to go over to the rod. Is the rod held by its end? The rod is held by its end. So what's the rotation axis of the rod about its end? 4/3 ML squared. Lads, now that we're here, what's the rod, guys? The rod is how long? It's of mass m, and how long is it? Length 2a. Mass m, length 2a, held by its ends. Okay, so it's going to be 4/3 ma squared. Okay, going to add the two red circles together. So what we're going to get is this one here added to this one here. So we're going to get I total. I'm just going to cut to the chase with this. I total is going to be 2m bracket a squared plus 12x squared. When you join them and factorize them, that's what you're going to get. Then you're going to use your t value equals square root of I over mgh. You're going to get t. We'll just go straight for t squared. T squared equals I over mgh. T squared therefore is 2m. 1 second. Yeah. Yeah. 2m bracket a squared plus 12x squared all over another m all over g. Now where's the h value coming out of, guys? The h value. Huh? Now there's no guarantee that the moment of inertia, there's no guarantee that it's at its center. Okay, so if we go back to the top, what does it say here? Momento length 2a can turn freely in a vertical plane. A uniform circular disc of mass 24 has its center clamped to the rod equals x. There's no indication. There is no language there to suggest that the center of the circle coincides with the center of the rod. There's no language there. So you're going to have to take the moments about m to sort that part out as well.